I'm here to talk to you about a topic that sort of summarizes what we do in my lab, and that's sort of lumped together under this title of the mechanical side of artificial intelligence. So I'm going to start off with a few definitions first to get us on the same page, and then I'm going to jump right into the best way I think I can describe our work is by example, and so I'm just going to go through 3 examples from our work that I think highlight the themes that I want to get across in this sort of notion of the mechanical side of artificial intelligence. So to start off, let's start with a definition that you're probably familiar with, which is the sort of maybe now classical side of artificial intelligence, which is basically having computers, robots, machines able to perform tasks which would normally involve the level of intelligence of a human. So things in terms of perception, autonomy, control that would normally require human intervention. And so this is a very old concept coined just down the streets at MIT. So that's not what we do. So in my lab, we do kind of the other side of this, which again, we call the mechanical side of artificial intelligence. To contrast this is developing new technologies, new robot platforms specifically, which make these questions of perception, autonomy, and control easier by virtue of their mechanical design, their material systems, their manufacturing strategies, et cetera. So we're really thinking about, let's build new robots that can make these sort of higher order AI concepts, make those things easier. And so how do we do that? So that's what I'm going to talk about for the rest of this discussion. But one of the things I want to point your attention to is that this concept is not new. In fact, I'll argue towards the end of this discussion that this is actually much, much older than what we think about usually today as artificial intelligence. Okay. So let's jump right in. So I'm going to illustrate, as I said, through examples. And the examples I'm going to give are in these 3 categories. So robotic insects, soft robotics, in particular soft robotics for deep sea applications. And then I'll talk about some more recent work in developing an entirely soft robot. So let's jump right in. Robotic insect. What do I mean by this? One good example of this is this device here, which we call the RoboBee. So this is a 80 milligram device which is supposed to mimic the key functions of bees. And when I say this is at relatively low level, so just understanding flight behaviors, understanding fluid mechanics, being able to translate these into bio-inspired designs, understanding how we can overcome obstacles in terms of how do we manufacture things at small scales, how do we develop actuators that mimic the muscle function and structure that we see in natural systems, how do we understand what sensors and sensor modalities we'd want to have for given tasks, how do we understand new computational architectures that would really satisfy the size, weight, and power constraints imposed by such a system, and then eventually onto power systems, power storage, energy distribution within this device, and then finally thinking about having lots of these things do interesting things in aggregate. This is, I'm not going to talk much about the application side. Why would we do this? The answer might be very sort of unsatisfying in the sense that the motivations from a sort of task perspective or an application perspective are going to be basically the same thing that anybody that's developing an autonomous robot is going to tell you. So basically, you put these things where you wouldn't want to put a human or an animal. Tasks that are repetitive, dangerous, whatever, that's where these things might find application. Maybe you can go beyond what you might typically see with, Packbots and Roombas and the like, by thinking about these things as very small, very agile, being able to get into nooks and crannies that you might not be able to get into otherwise. Maybe you can motivate things by having lots of distributed systems, distributed agents, which could increase effectiveness of coverage or efficiency of coverage, graceful degradation of failure. And maybe these things could be made so cheap that they could be disposable. But I'm not going to talk about all of that. Really, what drives us, what motivates us, is not those things. It's really the technological exploration that has to come about if we wanted to really do this. And I'll try to allude to this throughout, but and this is something that's directly relevant to our role in the Wyss Institute, is we're constantly trying to figure out if we can solve some of these things, if we can answer some of these questions, then what are those solutions good for outside of this context? And so I'll try to allude to this throughout, but for example, if we can resolve issues in microfabrication and small-scale actuation and sensing, then maybe we can make small-scale surgical devices better, more effective, more dexterous, more feedback to the surgeon, and we're doing that as well. And as part of this project, as I said, we have to answer all these questions. So the first question that we had was, how can we build something at these scales? So we have, on sort of one end of the spectrum, we have MEMS, micro electromechanical systems, and techniques that are derived from the integrated circuit industry for the last 5-6 decades that provide us with a suite of tools on micrometer or sub-micrometer sort of size scales. We don't really want to go that direction. It fits the sort of need in terms of the scales that we're interested in, but it limits us in other ways. It limits us in terms of the suite of materials that we can use, the sort of dimensionality of the structures we can build. 2.5 dimensional maybe we can get out of more sort of surface and bulk micromachining processes, but we really want to create rich three-dimensional objects with all sorts of degrees of freedom, articulation, et cetera, as you would have in the organisms that inspire some of this work. And most importantly, which is a theme that will come up over and over again in this discussion, is if we want to be able to build these things, we really don't understand them. We really don't understand, despite our best efforts and all the modeling that we can put on these things, the best way we can understand these systems is by build and test, and often to failure. And so we really have to have a process which is, with a manufacturing strategy, which is going to give us the ability to manufacture things on the order of days, whereas more MEMS-y type processes might be on the order of months. And so that may be the most important distinction here. Okay, so that's one end of the spectrum. On the other end of the spectrum, I'm sort of illustrating the construction of or assembly of a internal combustion engine. I don't want to operate in this regime either. I don't want to be assembling thousands of arbitrarily shaped components with feature sizes ranging from micrometer to centimeter, under a microscope. We consider this sort of the nuts and bolts approach to this. So I don't want to do that for reasons of yield and complexity, and maybe this is sort of intuitive. But I'm going to contradict myself because this is exactly how we started doing this. Another way to describe this would be the graduate student with tweezers manufacturing strategy, which pissed off a lot of graduate students and is really not conducive to building things on this very sort of short time scale. And it takes a tremendous amount of skill. This is basically a former graduate student that's has a surgeon-like skill and able to do this under a dissection microscope. And all of these pieces, if you can tell, are sub-millimeter or millimeter sort of range, and they're complex objects. It's not a Lego type system where you can just sort of click things together. And so this has a lot of problems. But really, the main problem with this is if you were to do things in this way, where it might take the most skilled student that I've had in my lab in terms of sort of physical skill and spatial reasoning and all of this, it takes him a few weeks to assemble something like this. The problem is then these devices become precious, and it doesn't really allow us to explore the rich design space that we would otherwise really want to explore. And so we set out to change this and explore new options. And so this is, I think, really where one of the first examples of this concept of sort of mechanical intelligence. How can we embody all of the motions that were being conducted by that student as he assembled that device? How can we embody them within a composite structure and have this all do all of these complex assembly procedures for us? And so for that, we took inspiration from two places. The first was Nobel laureate Richard Feynman, who back in the late 50s was prophesizing the many aspects of micro-robotics and micro-machines in general, talking about the economies of scale that you would get as you shrink down in size, talking about small systems building other small systems, building replicas of themselves, and so tiny hands building building robots. And so that was one piece of inspiration that we had. The other piece of inspiration was from my son, who at the time was very much into pop-up books. And so you could think about pop-up books as being these, everybody's played with these, right? These fantastically complicated structures that come about by very simple means, very, very simple, actuation, if you will. You unfold something, you push something, you pull something, and out pops these really fantastically complicated structures, right? This gave rise to this assembly paradigm that we call pop-up book MEMS, which is illustrated here. So now we have this device, which is sort of in the middle here. You can kind of see what's happening is, we have this sort of device that we want, and around it we have this thing we call an assembly scaffold, which is basically just a set of linkage mechanisms which, if I want a wing over here and an actuator over here and a transmission mechanism over here, then I can build the articulation, the motion that is involved with linking those components by folding. And so that's exactly what you're seeing here. Is what happens is we create this structure. I'm not going to have time to go into all the details of how we do this, but we basically take a bulk micromachining process where we take individual layers, and these individual layers can be anything. They can be metals, ceramics, polymers, composites, doesn't really matter. and we use a non-contact direct write laser machining process to make patterns, to make cuts in these individual layers of relatively thin materials. And we stack these materials together, create a laminated structure, which is what you were seeing as the video progressed. And this structure then had many, many layers. So 10, 20, 30, 40 layers of these constituent materials. And within this, we can also make these parallel devices. We can make mechanisms by folding. And so that's a very simple concept, but the implementation of it is basically if I have rigid materials surrounding a compliant material, that compliant material then describes a fold, describes a weakened region that we can then array however we want throughout this device and then create these linkage mechanisms which then can create arbitrary degrees of freedom. So I can get anything, think back to the most complex pop-up book mechanism that you've ever seen. We can do that, but we can do that now at arbitrary scales to very small, even smaller than what I'm showing you, to arbitrarily large if you'd want, although there's better ways to do things at larger scales. And so this has a number of nice features. And the features that this has are we can create anything, any complex mechanism or device, and this is not just hand-wavy. We can actually prove this. In fact, we work with some computational origamicists at MIT, Eric Demain, Daniela Rus, who we spent a lot of time talking with about these types of processes, and it turns out that it's provable that you can make any mechanism you want, any structure or any mechanism you want by this process of folding. So that's one nice thing. Another nice thing I already told you is that we can include any material you want. One question that I often get is, well, why don't you 3D print these devices you want to make? And that's a good question. Some of the challenges associated with scale aside, 3D printing techniques are typically limited in terms of the types of materials you can have and the material diversity you can have within a given part. This is not so. So we can have any arbitrary material combination you want. And in fact, in the video you saw, I didn't point it out, but within this layered structure are the muscles for this device. So we use piezoelectric actuators, and they're buried within the layers of this device. And related to that is these things, you could be scratching your head and saying, well, you're basically just making a multi-layer printed circuit board and then folding it. And that's exactly what we're doing. So we can actually have circuits patterned directly onto the surfaces of these things and create complex electromechanical devices that require no sort of post-assembly in their three-dimensional shape. And scale and variance, and so I think I hit all the highlights. So this allows us to build devices like this. This is a few years old now, but this particular design was quite successful. The next challenge then was design, and I'm going to sort of gloss over this because I don't have time to tell you the chronology of this. That it basically, with this process, with these types of processes in hand, now we can make devices like this in a matter of hours. I'm exaggerating it a little bit, but not really. I mean, it's a very quick process to be able to build these types of devices. Certainly very minimal manual labor, or you can go back to the very manual if you want. But we can build these things very quickly, and so we've iterated, over, dozens and dozens and dozens of generations of these types of devices, and trying to figure out, how do we understand, how do we move the wings through the air? Do we just do biomimicry and sort of try to recreate the types of motions and types of morphologies that we see in natural systems in flying insects? By the way, bees is just a metaphor. It's supposed to invoke the sort of social insect nature. These are more like flies, actually. Flies being the only order of insects which actually have two wings. And that was chosen partially for their agility, but also partially because two wings are easier than four. So then the question of design. So how do we actually think about designing these systems? And this is a very simple device. And the way that it works is I sort of cut the robot down the middle, and I have an actuator on either side, and that actuator is basically just a little artificial muscle that's sort of doing this. And that very small motion is then mapped through a flexure-based transmission mechanism. It's just a gearbox without the gears, because those wouldn't work, and I'd be happy to tell you that offline. And then that sort of little motion then gets amplified into this large flapping motion. And then the second, I think, interesting sort of connection to this concept of the mechanical side of artificial intelligence is there's a lot of passivity in this device. So when I started thinking about how do we build a device like this, we worked with biologists, and the biologist said, well, you have two wings, and each wing should do this sort of flapping motion and this sort of wing rotational motion. And so I'm an ignorant roboticist. I just said, okay, well, that means 2 degrees of freedom, 2 actuators per wing. But it turns out that's not a very efficient way to do this, because as you're actuating these devices, and we happen to actuate them at resonance for purposes of efficiency, it turns out you have a 2-input, 2-output system that you're operating at one of the resonant modes, and it turns out you're going to be throwing away energy into the other resonant mode if you do that. So anyways, we actually use a lot of passive modes in these devices. And one of the passive modes is this rotation. So we actuate this motion and allow this to be passive and just tune. This is mediated by a little flexure hinge, a little fold at the base of the wing that you probably can't really see here. And by tuning the inertia of the wing, the axis of rotation of the wing, and the stiffness of this flexure, we can get this sort of quasi-static rotation modes tuned to the appropriate phase relative to flapping to generate optimal lift. And it turns out after we did this, we realized, we looked back at the biological literature, and there's a lot of evidence that flies do the exact same thing. So I'm not going to talk a lot about that aspect, which I just alluded to, the fact that we can start to use these bio-inspired devices to sort of reverse the arrow of bio-inspiration and start to use these things to tease out biological hypotheses in ways that would be difficult with the animal, but that's an example perhaps of that. So this is kind of illustrating what I just said about the ability to individually address each wing. And so then the way that this works is I flap these things, and it's basically like an amplitude modulation scheme with cross product with the way a helicopter flies. And so the way that that works is I can control, I flap these things at resonance, so I don't change the frequency of operation, I just create bilaterally asymmetric amplitude changes, which then, if I have a fixed frequency and change the amplitude, I'm changing the velocity of the wing. The lift force generated goes as velocity squared, roughly. And so then I can do force modulation independently on each wing to create body torques. And the way I do that is by, if I have a larger amplitude on one side than the other, then I have a larger force on one side than the other, so I do this, right? And if I have if I sort of bias my motion fore or aft with respect to the center of mass of the robot, then I get a pitching motion. And then yaw is a little bit more tricky. I basically have to keep the frequency fixed and sort of have a faster downstroke than an upstroke. So I get this sort of paddling, I'm not doing this right, like that. I kind of get this paddling motion with asymmetric drag. All right, so I can build these devices. I told you about how we design them. So this is an illustration of the thorax, if you will, of these devices. And this is something by a former graduate student who is trying to inject more controlled degrees of freedom in the device. And so in order to do this, he was adding in things like, I don't remember all of the numbers here, but there's, I think, 4 parallel 4 bars, 2 spherical 4 bars, and 2 spherical 5 bars, all within a couple of cubic millimeters. And so this is, and then you can sort of see this in this device. And so you get a sense of this sort of rich sort of topological complexity and mechanism complexity that we can achieve using these devices. And it's hard to see because, thanks to James Weaver for making this image, but you can't see the materials here, but there's carbon fiber, and there's titanium, and there's polyimide, and a whole host of other materials. Okay. So we can make these things. Hopefully you're convinced now that we can make these sort of complex devices, bio-inspired devices on these sorts of scales. The next thing that we turned to in this project is how do we actually think about flight control for these things? So I haven't really told you about that yet, but we've spent quite a bit of time trying to understand the fluid mechanics associated with flapping wing flight, structure-function relationships. How do we understand how to design a wing? Is an insect wing exactly what we should be doing? There's a huge morphological diversity within insect wings. In fact, that's how insects are classified, by their wing shape, so to some extent. So how do we actually think about understanding fluid mechanics? I'm not going to tell you about that, but we've spent a lot of time developing strategies, both numerically, analytically, and experimentally to understand that. So we can control wing motions, we can control fluid forces. Now the question is, how do we control body attitudes? We've done this through this sort of schematic here. Just shows the sort of architecture that we have, which is doing things off-board, so having an off-board set of motion capture cameras. You can think about this as it's the same thing that's used in CGI, right, to make Gollum and I'm forgetting the names from the new Star Wars movie, but all where they wear suits of little retroreflective markers and then move around and then be recreated in CGI. So it's the same sort of environment, but now it's shrunk down, and these little markers are now on our little robots. And so that's what it looks like in reality, and you can't really see what's going on here, but there's the robot. If I do this now, thinking about what control actually means for these things, if I just plug these things in and turn them on, this is what happens, right? And so these are open loop flights. This is slowed down by a factor of 8. And I'm showing this to illustrate 2 things, or 3 things. One is that the open loop dynamics are very fast. So I'll show you this in real time in a minute. Well, I'll show it to you now. So that's real time. So the open loop dynamics are really fast, which is good. We want to take advantage of that. The open loop dynamics are unstable, which is also good. We want to take advantage of that. Insects are the fighter jets of the sort of animal kingdom, right? I mean, you've seen these things. If you try to swat a fly, you know this. They operate, very dissimilar to a passenger jet, where in the absence of active controls, if the pilot takes his or her hand off of the stick, it should, by virtue of positive wing dihedral, it should remain with a stable attitude. And so the antithesis of that are many flying insects. And so it's operating sort of on the other end of that spectrum, and we want to take advantage of that. But nonetheless, we still need to be able to stabilize this unstable system. And so I won't get into the details of how we do this. It dives deep into some control theory. There's some really interesting aspects of this and some not so interesting aspects of this, but it turns out using this sort of architecture, we can prototype whatever controller you want. The key things here are latency. So between sort of perception information that's coming, in this case, from motion capture, but we also have onboard sensors that we can put on now as well. Keeping the latency down between that information and your actuation is key. But if you do that well, then you can do things like this. Hovering is really particularly challenging because, as I said before, in the absence of active control, this thing is just going to fly out of control. And in the absence of forward flight, there's no hope of passive stability here. So you really have to be active. That last half second there actually just illustrated one of the nice things about operating at these sort of scales. You can crash these things all you want, and they're not going to break. So larger systems, certainly human-sized vehicles, but even these small drones and UAVs, you even come close to a wall and they're going to shatter, right? So not so in these cases, and this is due to the physics of scaling, and I'm happy to talk to you about that offline. We can also get much more aggressive with these types of maneuvers. This is something called iterative learning control, where by the fact that we can crash these things, we don't care about crashing these things. I'm exaggerating a little bit, but we don't really care about crashing these things, and so we can try to do these sort of aggressive maneuvers where this is trial 8 or 7, and the first 7 or 8 of these things have failed. They crashed into the wall, but you learn from understanding the dynamics of those crashes, of those failures, how to actually do this well. A little bit more recently, we've actually taken advantage of the relatively high payload that we have for these systems and developed some perching strategies that leverage active electroadhesive that we sort of put on the top of the device and allows us to sort of go and perch on whatever we want. And the motivation here is simple, is basically the energetics of flight at this scale are so power hungry, so energetically expensive, that you're not going to fly around for too long without expending your battery or whatever power source you have. And so perching strategies make a lot of sense for any real mission. Okay, so I'm going to shift gears here. So I should say a few words about where this project is, just in case you're curious. You'll notice that all of these videos had a tether, and they all had external motion capture. You can make batteries that can fit on board. Just yesterday, we got the control electronics and control board that'll go on board that are being integrated as we speak. And so hopefully those challenges will be resolved, and the tether will be cut and fully autonomous sometime in the near future. By the way, has anybody seen Black Mirror? So you're probably like, why the hell are you doing this? This is crazy, right? So yeah, these are 30, 40 years away from anything remotely practical, let alone doing harm. Another device that is a little bit more mature but relies on some of the same strategies that I just described is this device. It's very similar actuation strategies to make small legged devices, and these things have a number of nice features. We can make them fully autonomous. They have fairly high payloads, which is actually not surprising given their biological inspiration also has very high payloads relative to their weight. And they actually turned out to be some of the fastest robots on Earth if you normalize to body length. And they also happen to be very highly dynamic. So these are not particularly useful gaits, but they sort of illustrate the sort of highly dynamic nature of these robots. And this is partially due to their scale, and I'm happy to go into that a little bit deeper offline. I'm also not showing a result here because it's unpublished, but we can get them climbing on walls and ceilings as well. And one of the things that we're aiming for these types of robots is high-value asset inspection. So we're working with a company that is interested in having small robots go where boroscopes can't go, and basically go and inspect things, look for cracks in engines, for example, which would not require them to be taken out of service. So I'm going to move on to another example, which is entirely different, but hopefully shares some of the same themes. And in fact, I think this actually illustrates the overall thesis that I have about the mechanical side of artificial intelligence better than the rest, and that's soft robots for the deep sea. So this story starts off with this. And I want you to hear the...
Sorry. Zoom out. I'm not sure he's going to swim anymore. there, the commentary. Ah, there he goes, and it's sideways. He's swimming. I told you he'd swim sideways.
This is from friends at NOAA, who, and this is exactly what it is what it is. So this is a robotic arm on the ocean floor trying to do a sampling, trying to do a collection task. So there's a group of scientists and marine biologists who are very interested in both exploration, what's in the deep sea, what are in the sort of deepest parts of the ocean, we don't know. I mean, I could quote you statistics and stuff, but I'll save that for you. The other thing is, just generally speaking, there's a lot of reason to try to collect organisms from depths that go beyond what humans can reach, so beyond scuba or technical diving. And so those are things like, understanding how, mesopelagic organisms are reacting to ocean acidification or warming temperatures. And so you want to get these things and be able to sample them. But you also want to do this gently, not only just because you don't want to mangle the things like is happening here or like here. This is another example. This is, I believe it's a glass sponge. Yeah, okay, thanks. Where we want to be able to collect this, but with this sort of jaws of life looking thing, it's impossible, right? So there's no way to, not only is there no way to get it really, but even if you got it, its biology is going to be sort of masked by the stress that you just induced on it. And so I saw these videos when I was at a meeting of the National Geographic Society, and there was one of our now colleagues that was there, was trying to grab these things from the deep ocean and couldn't, and for these reasons. And so right around that time, we were starting to work in this sort of nascent subfield of robotics called soft robotics. And soft robotics is just what it sounds like, trying to make robots out of rubber. And so, and there's a number of reasons you might want to do this. If you want to make anything, I could start off with a question to you. If I asked you to close your eyes and think about a robot in a setting where a robot's going to exist, what are you thinking of? Where are robots practical? Sorry? Factories. So factory floors, assembling, welding doors on cars, whatever, right? So that's a typical and extremely successful automation example of robotics. But what do you not see in that vision? You don't see soft robots, but you don't see humans. You don't see anything soft. You don't see anything delicate near them because they're dangerous, right? In fact, you see cages around them such that they're not going to harm anything or anyone. And so the motivation for soft robots is kind of get away from that, to make robots that are sort of impedance matched to natural systems, to humans. We have some efforts in wearable robotics. There's a lot of efforts that are led at the Wyss Institute by Connor Walsh in wearable assistive devices. And so that's one sort of application area. It sort of gives you the flavor of soft robotics. And so we were doing this a few years ago, trying to figure out, well, if we're going to make robots out of soft materials, how do we make the sort of core components? So how do we understand, how do we make sensors and actuators? Very simple things. How do we make a motor equivalent but out of rubber? And so this is an example where it's just an elastomeric balloon that's being pressurized internally, and if you pressurize this thing, it'll change its shape. And then one of the tricks that went in here is if I start to reinforce this elastomeric balloon with inextensible fibers or any sort of inextensible material, then I can get extension bending coupling, extension twisting coupling. I can get all sorts of complex motions, and I can do this without control. So there's no control here. I pump in pressure and the thing deforms the way I want it to, the way I programmed it to. So this is, again, coming back to the original thesis involving this sort of mechanical side of artificial intelligence. I want to get away from control. I don't want to, I'll wrap control at a higher level around this, but at the lower level, I want to have things sort of figure things out for themselves. And so we were able to make these, this is just a simple example of an anthropomorphic hand, but nonetheless, we show that we can create very effective devices. And so we convinced the National Geographic Society to send us on an expedition. In this case, it was over to the Red Sea. It was with our collaborator who had this remotely operated vehicle where we basically cut the hand off of the arm that was on it and put our soft hand on it. And so this was the first example. Oh, this is a shameless plug back to the National Geographic Society where that's me showing, thanking our sponsors effectively. What we did was the first example of delicate manipulation at the bottom of the ocean. In this case, this was only a couple hundred meters, about 150 meters below the surface, where we're trying to grasp these whip corals. But it was the first successful. We were able to actually grab these gently, and there's a little cutter at the bottom here, snip them off and bring them back up to the surface. You can imagine go back a couple slides, if I have that rigid gripper system and I want to grab this thing and I am, you know, a couple hundred meters, even more in some of the videos I'll show you in a minute, a couple hundred meters below me, and all I have is visual feedback from the cameras. They're very nice cameras, but all I have is basically two-dimensional visual feedback from the ROV, and now the boat's rocking, right? So how do I do this really tricky sort of manipulation task? In this case, and maybe I'll play this again, in this case, it turns out to be a trivial thing in the sense that we take advantage of this concept that I said before about bending, twisting coupling, and I just get close enough and power this thing, and it wraps itself up into a helix and grabs this thing. And there's other types of examples that we had. This is more of a sort of broccoli-looking sort of coral where we can just basically give it a nice gentle hug. There's all sorts of features here which enhance the sort of gentleness of this. Come in, clip it, and bring it back to the surface. So that was a couple years ago. We then wanted to sort of expand this, and so we've basically been hitching rides on anybody that has a big boat. A couple times now we've been with Bob Ballard on the Nautilus and hooked up these soft manipulators to, in this case, this ROV Hercules. And so this is now, I think this is about 1.8 kilometers below the surface, where this is grabbing this Holothurian here, this sea cucumber, where this is something which is, you know, effectively the consistency of wet tissue paper underwater, but nonetheless we're able to very delicately grab it, pick it up, put it back down. We didn't bring it to the surface in this case because this was just an exploration mission of what we actually could do, but I take this example specifically as one of the most delicate objects I could imagine gripping, and in one of the harshest environments I could imagine doing this in. I throw a very dumb gripper. It's just a simple, you know, three-finger thing that I just pump seawater into, and I can do this task very well. I understand, and James can correct me, that these animals have a defense mechanism where they invert their stomachs as a defense mechanism if they're frightened. As one of my students said, sort of a take my wallets and leave me alone kind of thing, and this guy showed none of those. We can also grasp. These are things, by the way, you can kind of hear the banter of the ROV pilots while this is happening. A lot of times we hear like, oh, we would never go after that thing with the rigid gripper. It just wouldn't work. And here's one example where it's not necessarily a delicate thing. This is a crab, but we can now go down and grab basically whatever we want, and then put it back down unharmed. The last thing I want to tell you about is a project that we had with Jennifer Lewis's group, and it starts with the following fairly obvious observation, which is, sure, the end effectors of those things are soft, but you know, everything from here on is rigid. So your rigid arm and valve manifold and pumps and ROV, whatever, is all sort of classical, very well engineered, but nonetheless is sort of rigid-bodied devices. And so the question is, can we create robots that are entirely soft, where there are absolutely no rigid components? And so that's where we set out. That's what we set out to do, and that boiled down for us into some sort of sub-questions. Those sub-questions were, well, how do we create the core components for these things? And the core components of any robot might be, at least on the lower level, thinking about the mechanisms. We have sensors, actuators, computation, and power. So how do we do those four things? And so actuation I already told you about. We can create fluidic actuation, no problem. Sensors I didn't tell you about, but I can tell you about offline. We can do that fairly easily as well. But in terms of how do we think about creating a little controller that's soft? How do we think about having power that's soft? Certainly not traditional batteries. And so long story short is that we leveraged chemical power for these systems. So the fluidic-based actuators require pressurized fluid, gas or liquid. And so what we do is we rely on peroxide decomposition. So monopropellant decomposition, in this case hydrogen peroxide, in the presence of a platinum catalyst. And so it's a very energetic reaction, and I can tell you about the kinetics of this later, but nonetheless, the products of this are hot gases basically that are useful to power whatever fluidic actuator you want downstream. Okay, that's great, but that doesn't say anything about control. If I just sort of dump peroxide on a catalyst and then capture that gas, that's going to actuate me just fine, but it's not going to do anything with any sort of sequence or control. And so the second piece of this puzzle is leveraging many decades worth of progress in microfluidics and soft lithography to create fluidic-based control circuits. And so it turns out you can use microfluidic systems to create almost any sort of copy in a loose way to any electrical circuit that you might want. Circuit components, resistors, capacitors, and even higher order things like digital logic and sequencers, counters, comparators, whatever. I can do that all in fluidic systems. This is an example of what we used, which is a very simple example of just a fluidic oscillator. So I pump in a constant positive pressure, and the output is basically an oscillation of pressure on multiple outputs. So there's the architecture that we have, where we have this fuel, goes through this microfluidic logic circuit, gets broken down past the check valve into a catalyst site that then catalyzes this reaction, produces gas that then actuates these actuators downstream. And so this is where some beautiful innovation from our collaborators in the Lewis group came in. So this is a concept that they developed called embedded 3D printing, where you take what you're seeing here is a vat of uncured elastomer. And this uncured elastomer then is being injected with a sacrificial ink. And so there's all sorts of tricks that are associated with the rheology of this to get these to be stable structures even though uncured. But nonetheless, let's ignore that for a minute. They're able to inject this sacrificial ink wherever they want within the sort of structure of this uncured elastomer. And this eventually forms the vasculature, if you will, of this robot. So what happens is once this printing process is done, and so you're seeing the actuators and the limbs being printed now. Once this printing process is done, this whole thing is cured, and so the elastomer solidifies. Then you still have this sacrificial ink within the vasculature. It turns out that the silicone-based elastomers that we use are porous to water, and the pluronic that's used as the ink for these things will break down basically into water and then self-evacuate. So you basically have voids that are formed more or less for free at the end of this process. And so that's the vasculature, that's the main sort of internal structure of this device, and they also figured out ways to print platinum-laden inks as well to do the catalyst site as well. And then the last step, which you didn't quite see, but it's sort of illustrated on the top here, is prior to all of this, we use soft lithography techniques to create this microfluidic control system, plant that in the uncured elastomer matrix, and then print into that device as well. And so what that gives you at the end is this, which we call the Octobots, and this is a bit metaphorical. I would say, almost every single talk I've seen by somebody that mentions the word soft robotics shows an octopus as inspiration, which makes sense. And so that was our inspiration, I guess, in some ways as well. This is a robot now, and I'm going to use quotes purposefully. And you can see the components of this device sort of in fluorescence here, where you have your fluidic control system, a fluid reservoir, catalyst sites. You see all of this, the vasculature that make up the actuation sites. Okay, so how does this work? So here's the schematic again of this thing in operation, and here's what actually happens. So I inject a fuel, being done on the bottom left here on the bottom two videos, and the pressure from the fuel sort of expanding the elastomeric reservoir pushes the fuel through the control system. Then, like I said, it gets broken down at the catalyst site. It gets alternated between catalyst sites, and then downstream then gets alternated between actuation sites. And so at the end of the day, this fantastic robot just basically just does this. Okay. So I mean, we're very proud of this. We're very excited by this. This, I think, speaks very clearly to this notion of trying to do as much of the sensing, actuation, control, power, whatever, in hardware prior to actually wrapping a controller around it. It is the first entirely soft robot, if you will, again in quotes. And so we were happy about this, and this got published in Nature a couple years ago. But really, it's more about being provocative. I think that there's I want to end with this sort of notion. Who's familiar with this? This is called an automata, which was made back in the 1700s, unsurprisingly, by Swiss watchmakers. It's a piece of art, which is, if you sort of open up, look under the hood, it's a series of gears and cams and levers, which are all connected to this mechanism, which allows this boy to write out complex passages of text. Is this a robot? Is it programmable? No. It's programmable at design time, but not reprogrammable, certainly. So no, I'm seeing, you're shaking your heads. No, it's not really a robot, right? What if I were to go and buy a Baxter and put a pen in its hand and do all the path planning and control for the exact same passage of text and have it, react to the page and maybe have some vision system? Is that a robot? There's no wrong answer here, but yeah, I mean, yeah, that's a robot, right? So I guess the question I'm trying to get at is, at what point do we take this very simple concept that we had, this trivial controller, which is just sort of making this oscillation happen? Many groups have done far, far more complicated fluidic networks, thousands and thousands of valves, which you can equate a valve to a transistor in a very loose way. So we can get much more complex behaviors, if you will, out of these types of systems. And I'm not going to pretend to answer this question. This is the subject, I think, of some of the philosophy I work now. But how, at what point do we stop with this path of trying to increase the mechanical complexity and sort of at the potential expense of performance or not, and where do we sort of bring in decades worth of classical electrical controllers and AI that are very common in robotics? So that's where I want to stop. We work on a bunch of other topics that I'm sort of illustrating here related to artificial muscles, bio-inspired robots, ultra-fast motions. This is the sensors that I was alluding to before. We're working on projects where we're taking some of these microfabrication techniques to make small-scale surgical tools, endoscopy tools that have just finished animal trials. We can make self-folding robots, 3D printed robots that jump. This is also with James, and a whole host of other things that I'm happy to tell you more about. If you want to buy me a drink next door, I'll stick around. Otherwise, I'm very grateful for your attention, for your participation. Thank you again for the invitation.